Hi. So this time around we are going to start with sorting algorithms, and I think in the last time, although I said that I will cover randomized analysis of randomized algorithms, I may have missed that. So let's see. I think I will try to remember and finish it at the end of this lecture. So sorting. Okay, let's look at sorting. I think we all understand what it means. Some list of objects, or either primitive or complex objects, and you want it to sort in some shape or form, correct? So that's the idea. Okay, so insertion sort. How do you test that? You can test that by, once again, the idea of test-driven development. Make sure you write your test plan first, so that when at the end you can figure out. A basic idea would be when you kind of write them in a particular order, they kind of appear sorted, right? That's the basic idea. Okay, sample sort client 2. Okay, some more things. You can sort various kind of things, integers, strings, files, whatever. Okay, so you can sort various things. Okay, so how do you do that, right? How can you sort various things? In this case, he talks about, in Java, once again, talks about Java. There is a compare to method, so there is a comparable, there is a comparable interface, and if you have that what you can have your sorting algorithm just taken types of objects of type comparable, so that internally you can just make, when you want to compare two objects, you can just make a compare to call. And how does the compare to work? This is the interface. It returns an int, and the way it works is, okay, so let's talk about that. So before that, there's some concepts that we need to just quickly go over. Total order, once again, if is a binary relation that satisfies antisymmetry. What that means is, if v less than equal to w and w less than equal to v, then v is equal to w. Transitivity, a less than b and b less than c, then a less than c. And if something a should be less than equal to b, or b should be less than equal to a, right? One of them should be equal to true. And it works for everything. And he talks about this. It doesn't work in this particular case, right? Rock, paper, scissors. Okay. Now comparable API. Once again, if something is less, return -1. Equal, return 0. If it is greater than, return +1. Turns out Java has already implemented the comparable interface for most of its primitive and data types. So that's something is right there when you start using Java. Okay, so I'm not going to skip. I'm going to skip that. Some sorting abstractions. Okay, you can instead of doing all less, you can just do less. You can use Boolean, and you need exchange, because once you know that something is not in the right place, you potentially want to swap positions. So we all know this. Okay, so if it is sorted, you can use less. What it means is that a should always be less than equal to b. Did it correctly sort the array? No, the answer is no, because you want to make sure that these things that were returned initially to the algorithm were also got back, correct? So that's always remember that. And one more other things. Okay, so now let's dive into the sorting algorithms. I think here it's kind of interesting. Most of it is revision, but I think it's at least there were some things that I found a little bit that at least I had forgotten or I didn't know. So selection sort, we know what it means is, so this is the basic idea. In iteration, I find an index minimum of the smallest remaining entry and swap ai and a-min. What it means is, okay, in iteration this, first find out what is the smallest that exists in this entire n row, and then move that with 7, right? So 7 will be moved here, 2 will be moved here. So you have at least one element that is in the correct position at the end of one iteration, right? So you're kind of going to do this excuse me, starting from I is equal to 0 to n minus 1. He just explains that. I've already spoken about it, so I'm not going to talk about it a lot. But yeah, so what it means is, after every iteration, you'll have one element which is in its correct position. Okay, so we want some more code for it, and okay, as you can see, it uses how many compares. It will first start with so you're trying to find out the minimum element in all these n elements. So you will do n minus 1 comparisons, right, for between n elements, and you will find out the minimum and then do the swap, and then you will do it between n minus 1 elements, which means n minus 2 comparisons and things like that. So eventually you will need so many compares and n exchanges, right, because eventually you're going to exchange it at the start, at that position and the smallest position you're going to exchange that. So it's order n square, even if the input is already sorted, correct? Because so let's say if you already had a sorted input, what that means is this particular string, you will still compare A with E, etc, 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 and you do all these comparisons just to figure out, oh, A is it in its right place, and this is the minimum, and you do the same with E, L, etc. So that I think is interesting. Data movement is minimal, it's linear number of exchanges. Okay, so that's selection sort, the most simplest one. Some animations for it. Let's look at insertion sort. Insertion sort, the idea is then in iteration I, swap AI with each larger elements to its left. Okay, what does that mean? That the moment so let's say you are AI, right? This is AI. So with each larger element to its, if there is no element to the left, if there is no element larger to it at the left, you just let it be. You say that, okay, you are in its right position. There is nothing. You don't have to move anybody here. If not, then you will move things around. What that means is that 7. Is there any element larger to it? Swap AI with each larger element to its left. So you will to its left. To its left there is nothing, so you just let it be. But the moment you come to 10, okay, there is nothing, so that's also fine. Now 5, the moment you come to 5, you will see that, oh, these two are kind of bigger than me. Then you'll move these two around, correct? You'll move these two around. So in this case, something interesting. There are two interesting things happening. First is that you're doing definitely more moves because you'll move 7, 5, and you are comparing this with what? You're just comparing this with the elements to the left. The larger elements to the left. Okay, but now there's something interesting here. Okay, and we'll look at it. Okay, so now it talks about what we think we already know. So we've spoken about this. So in this case, the interesting idea is at any given time, this is a sorted array, right? If had this been the only array that you had seen, this is already sorted. So I think this is kind of neat. So it talks about some code. How do you implement that in code? Not too worried about it. I think we'll be able to figure that out. Okay. Now this is what is the mathematical analysis. To sort a randomly ordered array with distinct keys, InsertionSort uses 1/4 n square compares and 1/4 exchanges on an average. Okay, so this is interesting. On an average, and now this is random analysis of random algorithms. So let's go and actually take a look at as to how do you analyze that. But the basic idea is that this is the basic premise. Expect each entry to move halfway back, correct? And that's what is the premise of this. The moment you can see why an entry will move halfway back, you will see that, okay, why this is order 1/4 n square, and not n square by, and not an order of n square by 2. Some more examples here. Now the interesting thing about it is the best case scenario is just n-1 compares, correct? Because you are, let's say you start with A, you start with E. Is there anything? You just look at this element here. If this element is already less than E, you know that you don't have to go back anymore, right? Because let's look at the L. Now the moment you compare L to E, you don't have to compare L to any other element before this. Why? Because you know that E is already the largest element in these three elements. So if L is already larger than E, then L is definitely larger than anything else. So that's the basic idea. In this case, you're not doing n square compares, you're only going to do n-1 compares, correct? And that's the main thing, right? That's actually very important. This is once again on an average, you're only going to do in this. So now to figure out why that was 1/4 n square in the selection sort, you would necessarily compare, the moment you are at this particular element, you would compare this element with everything here, right? And then you'll take n and you'll compare m with everything here. That's how the algorithm works. But here, on an average, you will find with a particular element here, you will only make one compare and not this entire chain, because this entire chain is already, the moment L is already greater than this, you only make one compare. And you can imagine on an average, half of these elements will be greater and half of them will be less, so you'll have to make these compares. Correct? I'm sorry I had to take a brief break there, but the basic, okay, so I hope everybody got an idea about what we were trying to talk about. So as you can see, on an average, an element there will be 50% chance of it already be in the right place. You will not do any more compares. You will only do one compare. And for a particular element, you will do n-1 compare. So on an average, it will be half of selection sort. Hence, it's n squared by 4. So that's the basic idea. And in the worst case, yes, it will do n squared. So now let's quickly look at the randomized algorithm here. Once again, here there is some more examples about neat animation. You can actually just go to this website and look at the animation. So let me show you and this is for randomized algorithms. In this case, once again, I'm referring to the same lectures, lecture 61B, and once again, I think these are good lecture notes that you can look at. Basic idea here is expectation. So we spoke about expectation indirectly. So I'm just assuming that you know these terms, probability and expectation here. In this case, it explains as to what is the expected number of comparisons you tend to make, right? So the expected number is half that of selection sort. So that's the basic idea here. Correct? So hash tables, okay, so once again, we are using the hash table example here, and I think in this case he's explaining quick sort, why that is order n log n, okay, and that's the idea. But I hope you get the idea of expectation, right? So in your mind you should figure out what is probabilistically, and then in terms of probability you can figure out an expectation for something and then figure out the calculation. So once again, this means on an average it will take n log n, or on an average it will take n squared by 4. It doesn't mean that it will always do that. There is always a worst case when it will take order n squared. Okay, so we go about this an insertion sort for partially sorted arrays. In this case, okay, I actually kind of forgot, but definitely if there is number of inversion, okay, yeah, I know this. In this case, the number of inversions is the number of swaps. So in this case, these are the kind of elements that are out of place. There are 6, and the idea is if the number of inversions is, if it is partially sorted, if the number of inversion is less than equal to some constant times n, when n is the size of the array. As you can imagine, there can be more than n. There can be lots of inversions. And in this case, an array of size n with only 10 entries out of place. For partially, the insertion sort runs in linear time, correct? So in this case, what that means is number of you are just exchanging things. In insertion sort, what is going to happen is that you're just going to move some elements around and it will run in linear time. Okay, some more example here. Okay, so we looked at selection sort, we looked at insertion sort, and now let's look at ShellSort. So the ShellSort, the idea is that move entries more than one position at a time by edge sorting the array. Okay, so what does an edge sort array mean? Okay, so we'll look at this. So this is kind of interesting concept, right? So first you do 13, and we look at these numbers. Okay, this is what this 13 is 13, 4, and 1 are kind of magic numbers, and there's some talk about that at the end. So let's look at a real example. You initially start with 13. You initially start. Okay, so let's look at this. So this is the idea. You look at 7 sorts. So let's say there's some array of element of length n. You start with 7. So you start with S and M, and you sort them in between. Then you start with in this case these are the elements that get swapped, right? When you look at 7 sort, correct? Now when you start with 3, you say, okay, now let me look at M and E, the third element after that, correct? And now should I swap them or not? In this case I have to. Then you start with this one and this one. Okay, do you have to swap them? Yes. And so on and so forth. And finally you do, okay, just swap elements next to each other if needed. And finally you have a sorted array. So what's happening here, what are these magic numbers and how do they work? So the intuition, or to figure out why that works, is that a G sorted array remains G sorted after H sorting it. Okay, what does that mean? A 7 sorted array, so once you have these elements sorted in the right place, correct? Like, okay, the elements S and M, which are 0 and 0 plus 7, are either correct. These, whatever these elements are, they're in the right sorted place, correct? If you now try to sort them sort smaller elements, they will still, you will not mess that up. That's the idea. You will not do anything that will screw these two elements. These two elements, whatever they be, they will be in the right place. It is a little bit more subtle, but we'll take a look at that later as to why that works. Well, this is, and it's all about these magic increments, and it's I think Donald Knuth proposed 3x plus 1, that you start with these kind of things, and professor came up with this set of implementation, with this set of indices. But once again, the way I think about this is, these are, I think this is beyond the scope of this course as to how do you come up with these numbers. Okay, so now how the implementation, I am not going to get into that in detail. It basically says that, okay, you start with some sequence and you constantly reduce H by 3. That's the basic idea. And H is the is the H sort that you're trying to do. And inside this you do an insertion sort, correct? So that's the basic idea. And okay, so it now gives some more examples, animations, and analysis is interesting. The worst case compares used by ShellSort with 3x plus 1 is order n raised to 1.5. Okay, so it's not order n squared, it's order n raised to 1.5. And the number of compares used by ShellSort with 3x plus 1 increments is at most a small multiple of n times the number of increments used. Okay, so those are, I think these are key analysis. I think that maybe I should do some more justice about ShellSort. Let me read that a little bit and maybe add that as an addendum to this lecture later. Okay, why are we interested? Okay, I think it's just a simple idea, and it shows how that leads to substantial performance gain, and some good algorithms are still waiting discovery because we don't know what the correct set of numbers are. Shuffling, I think this is very important. We think that, okay, what is shuffling? Given any card, let's just assign, let's shuffle these. How can we shuffle them mathematically? And the idea is you can potentially assign them a random number and then sort them in that random number, and it will be shuffled. But then that is pretty expensive. Can we do something better? Turns out we can. Instead of doing that, what is this word theory? Okay, last 50% of the time. Okay, so there were some things here. Browser should okay, we'll talk. Okay, so as you can see here, there's some problem here. Shuffle sort by making compare always returns a random answer. Compared to browser that should implement a total order. This was not good. Okay, but let's look at shuffle demo. How do you do shuffle? I think this. I just want to show the order n shuffle. I completely missed that. Okay. Okay. So the idea of order n shuffle is that you shuffle between O and okay. So given in iteration I, pick integer r between O and I uniformly at random and swap AI and AR. That's the basic idea. The moment you do this, this will produce a good random shuffle. Okay, so once again, there is you want to do this. It's an order n algorithm for shuffling this, you know, to produce a good shuffle and a good random shuffle. And the idea is, given array of size n, you start with, you know, iteration 0, 1, 2, etc., and with iteration I, pick a number r between 0 and I, and you shuffle them. Now the interesting thing here is, why is this important? You know, why should it be between 0 and I and not between 0 and n all the time? There is a very good article that actually explains this in detail, and you can look at it. It's the Coding Horror blog, and you know, this is, you can just search for it, The Danger of Naivety, and it actually explains why that is important. You know, why it should be between, why should you swap between 0 and I, not between 0 and n? And I think here is kind of the interesting idea. Here's the interesting idea. You know, he explains why did he, you know, what happens when you do it between 0 and n. It turns out you actually skew the shuffling. Okay, so if given between, so the idea what he uses is that, let's say there are 3 cards, there are 3 factorial possible, you know, combinations of that deck, right? And what that means is 6. And when he actually, when you use 0 to n, you see that some combinations are more likely than the others. And why is that the case? Why is the naive shuffle algorithm bias and fundamentally broken when you do that? It's, and you know, he says that why the Knuth, Fisher, Yates is between 0 and I. And the idea here is very simple, that the naive shuffle every time will try to do between 0 and n, which is 3, and the Knuth shuffle, when you do between 0 and I, will always reduce. So in this case, it will shuffle between 3, 2, 1, which is 6, which is 3 factorial, which is the right number of permutations. And here it's trying to shuffle between 3, 3 and 3, which is 3 raised to 3, which is far more than the actual number of combinations that are possible, permutations that are actually possible. And turns out when you shuffle more than what is needed, it doesn't actually improve, but hurts the shuffling. And that's the basic idea here, and it talks about in more detail about what happens, and you know, here's the idea. But more shuffling gets worse, not bad results. That's where it goes horribly wrong. Okay, so yeah, you know, take a look at this blog for more details, and there's lots of graphs, and it explains it much better than what I can do it quickly in this lecture. But yeah, do take a look at the blog. Okay, so we know why this shuffling works, and you know, and yes, if you try to use between 0 and n, why would you screw things over? Shuffling, ConvexHull. The last problem is about ConvexHull. In this case, professor talks about what kind of places our sorting algorithms show up. In this case, the problem is that given a set of points, you have to find out the smallest convex set containing all the points. Okay, so that's the idea of a ConvexHull. It's a geometric, it shows up in geometry all the time. And once again, here there are hard cases. What that means is, if in this particular line, if these 4 points are collinear, you don't want to pick points whatever A and B, you only want to put points, let's say these two, right? Because these two are not needed to mean the minimum set of points. And how do you go about doing it? You can imagine stretch a rubber band or something like that. But then in this case, okay, you don't want to stretch it like this, you want to stretch it like that, and things like it. And what are the applications of ConvexHull problem, farthest pair problem, etc. are extreme points on the ConvexHull. This is where you can find things out. And it has some geometric properties. The geometric properties it has are interesting, which will actually help to solve the problem. That given this, start with P and an angle, yep, and the angle between this. The vertices of the convex hull appear in increasing order of polar angle with respect to P with the lowest y coordinate. What it means is, look at this vector, and then vector 1 to 5, and 5 to 9, and 9 to 12, and then this one is not considered. So you're always going in a so there's one important thing is you're always going to counterclockwise direction, correct? And it's increasing order of polar angle with respect to P, correct? So that these are important factors. So how do you go about doing that. So you start with P, the smallest. Given all these elements, you start with the smallest, the element which has the smallest y coordinate. You need that, and then you find out the next element in terms of, now you look at the angle theta. You find out, okay, 1, and then you say, okay, 3, maybe 3 is 3 goes counterclockwise, so maybe it is actually part of the convex hull. But the moment you go to 2, which is the next element, you will see that, oh, you're no longer going counterclockwise, so you have to ignore 3. Now you come to 1, and now you come to 4. Okay, maybe 4 is, but then the moment you go to 5, you're no longer going counterclockwise, you're actually going, clockwise. In this case, you have to ignore 4, and then the same you'll have to ignore 2, and so on and so forth. So you have to now join 1 and 5. Now you may take 8, but the moment you take 8, then if you have to go 9, you actually go clockwise, so you have to ignore 8 and things like that. And that's how you can figure out the convex hull. So we have to sort for multiple things. How it is counterclockwise. How do you know whether it's counterclockwise? So this is basically some basic idea is that, okay, you can do some you can figure out by a determinant. That's where you will know, and you just use that for your mathematical algebra. So that's how given 3 points, how do you know that it's a counterclockwise turn? You want to figure that out, and that's pretty much it. Okay, thanks. See you in the next lecture.